The other day in class, I had mentioned the idea that the two sample t-test um, was very robust. And I'd like to give you kind of an example of what I mean by, when a test is robust or not. So to illustrate, I'm using an applet from the Rossmann Chance collection, and I'll leave a link to this app in Schoology. What it allows you to do is it allows you to kind of sort of create two kind of hypothetical populations. And so I've chosen two skewed right populations. My first population has a mean of 10 and a deviation of 8. And my second population has a mean of 15 and a deviation of 10. So a little more deviation in the second population. So these are skewed to the right. And what I'm going to do, or what this applet is going to do, is I'm going to take samples of size 10. So I'm going to take 10 things from this population, and it's going to graph those 10 observations right here. And then it's going to also take 10 items from this population and graph them here. So let me kind of set this number of samples to just 1 for now. Let's just see what one sample looks like so you can see what this is doing. So I'm going to click on Draw Samples. Okay, so what this has done is it's grabbed 10 items randomly from this population, and as you can see, this is this distribution looks pretty skewed, and not a surprise because you're pulling it from a pretty skewed population. Now the average in this sample is about a 9.089, which again is not much of a surprise because the population is centered at 10. So the sample should be close to that as well. And so then what's being recorded here is that 9.089 is being placed right here. So this is where the sample average is for this first sample that I've taken. And it's doing the same thing down here in the bottom. It's taking a sample of 10 items from here, and here are the 10 items. And also notice that this one is also skew, maybe with an outlier. Again, not a surprise because when you're drawing from a skewed population, you tend to get samples that show some skewness and maybe even outliers. The average is about a 13.45, and again, 15 is the average in the population, so nothing, alarming right there. And then this average of 13.4 is graphed right here. So the last graph, though, is saying, okay, what's the difference in the samples? If I took the sample average for my first sample of 10 and subtracted the average for my second sample of 10, I get a difference of about negative 4.369. So this average minus this average. So this is keeping track of the differences. So I'm going to be generating a sampling distribution from just drawing from population 1, a sampling distribution drawing from sample 2, and I'm also going to get the sampling distribution of the differences. Okay, so this is kind of like the 2 sample distribution. Each of these is like a 1 sample distribution. So now I'm going to go ahead, instead of grabbing one at a time, I'm going to change this to say, let's grab 500 samples. 500 samples of size 10 from here, 500 samples of size 10 from here, graph the sample means, and also graph the differences. And so I'm going to select Draw Samples. Okay, and so here's what we have after, I guess now 501 samples have been drawn. This is the most recent sample, the 501st sample from this population. Again, it has about 11.8 average, and so that 11-point average has been added to the distribution of sample means, right? This is a 1 sample distribution. I'm also keeping track of the 1 sample distribution here, and then also keeping track of the differences in the means. And here's where the idea of robustness comes in. You will notice that for just population 1, the sampling distribution for the first population still has some skewness to it. Okay, you'll notice a little bit of skewness in the sampling distribution, and that's because we're only sampling 10 items. This is a pretty small sample. We usually like to maybe get for skewed populations, we'd like to maybe get, over 20, 30, maybe even close to 40, depending upon the degree of skewness. So sample size of 10 is a little too small if we want this to kind of tee out or norm out. So too with this sample. This one also shows some skewness. And again, that's because we're only taking 10 items from a skewed population. And so we're going to get some skewness in our sampling distribution. But if you look at the difference in means, right, the two sample distribution, you don't notice the same amount of skewness. If anything, this one seems to be kind of getting pretty close to a T or a normal distribution. And this is what we mean by robustness. Even with small samples of 10 and 10, the difference in the two means, the distribution of that anyway, tends to kind of norm out or tee out a little more quickly. Whereas these ones definitely have got some skew in them. So in a one sample test, either this or this, you still have skewness with a sample size of 10. But when you look at the two sample comparison, the two sample means, you don't have that same degree of skewness. And this is when we say the two sample t-test is very robust. It means you really don't need as big a sample. The 1540 rule, the rule that's, whatever, the 1530 rule, you can sort of bring those numbers down a little bit. You may not need as big a sample as you think. So let me go ahead and draw another 500 samples. Okay, draw samples. So now this is after 1,000 samples have been drawn. And again, we still see some skewness here and here. And this one is still a little uneven, but I'm looking tail-wise. They don't look a little different. Now this thing looks like the center might be a little off, so maybe let's do another 500 samples, and then maybe another 500. Let's get ourselves close to 5,000 samples. And after 5,000 samples, okay, we're definitely, the skewness is staying here. Because again, these are only samples of size 10 and skewness is staying here. But over here, you don't see that same skewness. You start to see kind of a nice symmetric distribution. This is suggesting to me that for this particular situation, samples of size 10 seem to be pretty good for if you want to compare the difference in the means, that samples of size 10 might be enough. Now, I got to tell you, one thing about robustness, these tend to be very robust, especially when the sample sizes are about the same, like 10 and 10, is when you have samples like, say, 10 and 20, or maybe you sampled 10 and only 5, okay? Usually when you get more than a 2-to-1 ratio in sampling, you start to lose that sort of symmetry. It starts to kind of skew a little bit. So it's not quite as robust a test when the sample sizes are kind of more than a 2-to-1 ratio from one another. I'm not quite sure why that is. But the idea is you want to try to, if you want to maintain the robustness of the two sample test, it's a good idea to try to keep those sample sizes the same. So let me go ahead and try to see if I can reset this. And I want to take an example that we were doing in class the other day. So reset. I'm now going to take the killer exam problem we did the other day. With midterms versus final. And so I'm going to use the sample statistics. So for the midterms, okay, that looked like the average was about I'm just going to call it about a 71. And then the sample deviation was about an 8.56. So I'm figuring the population is going to be a little more than that. So maybe I'll call this a 10. Okay, and then I'll go down here to the final exam. The final exam was about a 68 average. 68 average. And let's see, the sample deviation was 11.3. So let's make that a Let's make that about a 12. Okay, so let's see if this will adjust things for me here. Well, it looks like it didn't want to adjust, so maybe I need to refresh this. Let's see if I can refresh the screen. Thank you for your patience here. Okay, let's try that again. So let's set these to skew right and skew right, and then let me set the numbers again. Okay, so 71, and let's call the standard deviation about I think I said a 10 before, 10. Okay, let's see if that'll, okay, it doesn't seem to want to change the scale for me, but maybe, let's see what happens when I do this. Let's call this 68, and let's see if this will adjust up to, let's say, 12. Sampling options. Okay, there we go. Now it adjusted for me. So, okay, skewed right distribution, 71 and 10. Those were my midterms. And then here are my finals. This one had a little bit more skewness. So they're not severely skewed here. But the question was, in the midterm final problem, we took 10 of each. And we were kind of wondering whether those sample sizes would be appropriate. So we're going to take a sample size of 10 from the midterms, and we'll take a sample size 10 from the finals, and let's see what happens. So let's go ahead and do, let's take one sample first of all, just to make sure it seems like it's kind of working right. So let's draw the sample. Okay, so we ended up with kind of a skewed sample, a skewed right sample, and that's kind of what happened in our midterm scores from before. The average on this time was a 68, okay, which was a little different than what we witnessed last time. And then this one's also showing a bit of skewness at 71. And so then the difference is a negative 2.5. The final exam in this case happens to be a little higher than the midterm score. But let's go ahead and try now 500 samples. So let's go 500 and click on draw samples. Okay, so let's see what's taking place here. So there's 500 samples. Okay, let's see. With this, hard to tell if there's some skewness in this one. Definitely some skewness here. I'm not seeing the same skewness. Let me do another 500 samples. Let's maybe kind of get near maybe 5,000 samples. Probably usually a good idea to get like lots of samples before we can see what's happening in this problem here. So, okay, so these are samples of size 10. So this one seems to be pretty good, even though the population was skewed to the right. It wasn't severely skewed to the right. So perhaps I've got my deviations a little too low for this situation. And then this one still maybe a hint of skew here. But again, the big takeaway is notice that the differences, again, that skewness is not so apparent. So once again, this is what we mean by robustness of the two-sample t-test is even though each individual sample, its sampling distribution may not be nice and symmetric because the sample size is too small. When you kind of subtract one from the other, it tends to kind of tee out or norm out a little quicker. In other words, you can get away with smaller sample sizes in the two-sample test. So again, I'll leave the link to this applet up. You're welcome to play with it and just sort of try different population means and deviations, and you could kind of watch and see how everything kind of evolves. I think it's a great tool to kind of develop a sense of when is my sample big enough, when might it be a bit too small. So we'll talk more about this in class, but otherwise, thank you for watching.